Welcome back to the Cycle World podcast. Well, we're back anyway. If it's your first time, thank you for joining us. I'm Mark Hoyer. I'm the editor-in-chief of Cycle World, and I'm with Kevin Cameron, the technical editor. And this week's topic is how aircraft engines improved motorcycles. What do aircraft engines have to do with motorcycles? Before we get into that, this episode is sponsored by Mecum Auctions. Mecum is doing the Las Vegas Motorcycle Auction. It's the 35th annual auction in Las Vegas for Mecum. It's huge. They've got usually more than 2,000 motorcycles. There are 50 collections coming through this year. It's the biggest motorcycle auction in the world. Bidder registrations are open. I can't recommend this auction enough. Now, Mecum is sponsoring us, but I would go anyway. And I would recommend it anyway. So we're very happy to have them as a sponsor because there are so many reasons that I love going. And one of them is that there are 2,000 motorcycles and there are multiple examples of everything that you would ever want to see. If you want to see a lot of Vincents, you can go see most of the Vincents. If you want to see an XS 650 and I wonder if there's supposed to be washers under that, you can find some either incredibly original XS 650 or one that's been restored to an nth degree, and you have a reference and you can go there and take pictures, and they're just you can't even believe it when there's sort of the rodeo area where it's the big stands and the big the auction block where they roll everything across and they've got the big screen, and it's mental the way that the auctioneer runs the show. But there's the whole area in the back. It's like the warehouse, and it's full of all the bikes, and they're just parked, and you can go look at them because you got to look at them if you're going to bid on them. You don't have to go, but you should go. You can register and bid by phone. You can bid online. You can do all that stuff. They're adding more bikes. Kevin and I are going to do a podcast in a couple of weeks that will be our picks from the auction. We'll get over those. It's bring the family. It's really fun. And for me being in the industry, you get to see all of your friends, all the collector guys. There's Baxter Cycle shows up. He's a great guy, and he brings bikes to the auction. And there's a guy, Leo Goff, who's an engine guy or restorer. He used to drag race. He's in the Memphis, Tennessee area. He always goes. It's just a great place to gather and talk motorcycles. It's at the South Point Hotel and Casino. It's a great place to stay. It's huge. There's rooms booked now. Get in there. You can watch the live block cam on the website. TV, Roku, Mecum TV, Roku, Thursday, and I think they have added an extra day to the auction because it's really loading up with a lot of killer stuff. Join me. I'll be there. It is January 27th through the 31st, or possibly an extra day, 50 plus collections, etc. So anyway, thank you, Mecum, for sponsoring it. Thank you, audience, for checking out Mecum. All the stuff's in the description, and tune in for our collection podcast because it's a lot of fun. We pick bikes that we want to talk about, and Kevin picks them for some reasons, and I pick them mostly because I don't know, I like pizza, where Kevin's sort of very doctorial about his the historical significance. I'm like, I really liked that when I was growing up. I want one. It's a good time. So join us. Thank you, Mecum. All right, Kevin, aircraft engines. So we were talking about the topic here, and just the very fact that we said, well, what if this is a topic? And then off we went. We just started blabbing, and we thought, well, that's a pretty good topic because we haven't made really, we have a lifetime of research about this, more you than me, metallurgy and all the things that change. But the thing that strikes me about aircraft design and Kevin will kind of illuminate all this, but the thing that strikes me is aircraft design is peculiarly honest. It has to be. And Kevin pointed out in our conversation that it has to be light enough to fly and heavy enough to make it. And the light enough to fly part is the honesty and the authenticity. It's just enough material to cover the working internals. It's not extra. It doesn't have it doesn't have covers that are supposed to suggest a certain feeling. Like when you put a fairing on a motorcycle, you can kind of shape it however you want. It should have some aerodynamic something about it, but we just put fairings on bikes and we make them really pointy if that's what the style is, or they're very curvy and flowing if that's what the style was. It was style. MotoGP fairings, functional, right? That's the way they look, is that they're highly functional. They got all these wings and ground effects and stegosaurus things on the tail sections. It has a reason, and in that way we kind of like it. But aircraft is honest and shrunk down, and you see the shape of the crankcase, you see where the push rods are going, you see the taper of the fins. There's just enough to get the job done that it was designed to do. And that's what I love about it. And that's to me, that's what the best motorcycles are made of. If you look at a dirt track bike, it's very much a land-bound aircraft. It has a purpose. It's meant to be light enough, and it's meant to do certain things. And it's just enough. And I think that's what's so essential and beautiful. What do you think, Kevin?
Well, the motorcycle, of course, is an engine, two wheels, and a place to sit. And there's a lot of nuance in all those elements. But although you can add all kinds of things to a motorcycle that are on there for artistic or emotional or socio-political reasons, when it comes down to trying to get around a circuit very quickly or building a ride you can stay on all day long and be ready for the party at the end of the day, that takes some doing. And there isn't room for extra. Aircraft, anything that is required to fly has to pay its way, because otherwise it is subtracted from the payload. So, for example, if the engines are going to have to be fueled on an inferior gasoline, inferior to what they were built for, they're not going to develop the power that they were required to, because they can't push on into knock with a supercharger boost. So you're going to use more runway. You're going to be running the engine in a different manner, so that your range suffers, your payload suffers, and ultimately it can become unworkable. So in the early days of aviation, getting in the air was the big one. And that's what the Wright brothers did. And then the French, 1908, 1909, the Wrights gave some people rides. I think Glenn Curtis did it. And then everyone wanted to go. So they began to build the beginnings of airliners. Some of them were pretty boxy and strange looking, and they had wicker chairs inside, because look around, what's lighter than wicker? Used to be wicker sidecars, right? So,
Well, nature's composite.
Yes, that's right. It was all very much cut and try, and that's what motorcycles were as well. The two Werner brothers, Russians working in Paris, tried putting an engine into a bicycle every place that they could. Beside the rear wheel, on top of the rear wheel, on the handlebars. That's where the Solex ended up, driving the front wheel through a roller.
Yeah.
And presumably blowing oily smoke onto your person. And ahead of the down tube, that's where Minerva liked it in 1903, or above the bottom bracket, which is where it's ended up. And cut and try. They tried all those things. There was another outfit in Czechoslovakia that ran through the same set of experiments, because they wanted to be sure they weren't overlooking something. And there are people who have written theoretically about motorcycles, but it's because it's a simple machine. It's quicker just to try it. So, because if you develop a math model, then you have to validate it.
Yeah.
You have to, it predicts this. Well, we'll build that. Oh, oops. Must have left out a term. So anything that flew became very spare. The rotary radial engines, by rotary, I mean that the cylinder, all the cylinders and the crankcase whirled around while the crankshaft was bolted to the firewall and did not rotate. Now, the advantage of this is that it doesn't vibrate. If you couldn't balance the cylinder assembly because it's axisymmetric, and that was a great thing in early airplanes because they were made out of sticks and cloth with
cables,
wire bracing to sort of hold it all together. And the cylinders on early Gnome rotaries were machined from solid steel, and they were machined away until there was practically nothing left of them. We've all heard the jokes about he bored out his engine until it was just a stack of washers, meaning that the cylinder itself disappeared. The boring bar turned it into dust.
Oh, it's the joke my friend Bill liked to say about his Trail 90 that was taken out to 110 or something. He said you could see the shadow of the cylinder or the piston moving in the engine.
So the temptation was to machine anything that was going into an airplane because then you could control all the thicknesses. Well, that didn't work out for complicated shapes like crankcases, cylinder heads, and so forth. And so for a long time, those parts were cast. That is, liquid metal was made to fill a mold whose cavity was the shape of the part you wanted. And you had to use the shrinkage rule for the material you were pouring because it would tell you how what's dimensions you should make the cavity so that when it returned to room temperature, it would be the size and shape that you wanted. Lots of little details were uncovered when engines were made to run for long periods of time. Ball bearings suffered fatigue failure. One of the biggies was cylinder hold down bolts. The problem there is that the bolt isn't very long. You can tighten it up until it starts to get loose, torque to yield. But it doesn't have much elasticity, so that if there's a gasket there and the gasket compresses, you can lose all the preload and the cylinder is just sort of sitting there. So also they found that the hold down bolts or studs broke constantly. Now this was a huge thing in the time of World War One. The French and most of the Continentals used a lot of rotary engines. The Germans built a lot of inline sixes that were liquid cooled. But this problem with threaded fasteners is that in the beginning, threads were cut with a die. What crudity. I mean, it works for a lot of low stress operations.
Yeah, your swing sets and
yes.
You can go get your grade 5s. That's fine. But rolled threads. It reminds me when you talk about cutting threads. It's kind of savage. It works, but you're taking your die and you're like, and it's cutting the steel or whatever your fastener is made of. I've seen that high speed video where they put a camera on a lathe or it's a milling machine or something. And it's a high speed kind of like microscopic camera. And it's showing you the cutting of the part. And it is savage, even though it looks like, oh, here's the chips. And when you set your lathe up really well and you've got a nice sharp tool and it's in the right spot and you can get a long chip that just goes forever. It's just peeling off the whole thing. It's not flying.
Do not take hold of it and try to pull it off the
No,
lathe.
no, no. But it seems wonderful, and if the machine is in good shape and you're making that finish pass, especially, you can end up with an incredibly shiny, seemingly perfectly smooth piece. But at the microscopic level, it's really savage. Like, you can find this on the interwebs. You can find that cutting video. It's just, oh man, it looks so hard. And when you roll it, you put that surface into compression.
Into the 30s, into the 1930s, Wright was still doing ground threads for high stress fasteners, and they were still failing. And of course, when you grind something, you can make the surface finish finer, but ultimately it is the result of scratching metal off of it. And so the process of rolling threads recommended itself because then the threads are forged. The surface of the metal is compressed, which you want because things fail in tension. So if you've got the surface in compression and you begin to apply stress, first you have to overcome the pre-existing compression in order to get no stress, and then you have to stress it even more to put it into tension. So rolled threads forge the material into the shape that's desired, and the threads are forged. They are not torn, i.e. cut. And they have even developed now methods of forging internal threads for the same reasons that for example, the cylinders on Wright's giant 3350 that powered B-29s in the war, powered the Sky Raider in Vietnam. Its cylinder is for steel forging and upset with an integral flange at the bottom, and it is bolted onto the crankcase. Naturally, like a motorcycle engine, starts out with 4 studs. What happens if you blow head gaskets? You go to 6. Then you go to 8, 10. Wright took it all the way to 21, which was all that they could cram into the flange. And every last one of them, the bolt came down on a part spherical washer that rested in a part spherical seat machined into that flange, so that when there was relative motion, and there always is, because when the engine fires, 32,000 pounds of force try to uproot the cylinder, which means that the flange holding it down is bending down, and the mouth of the crankcase is bending upward, which means that the fasteners are being tilted. That's why those part spherical washers are there, to allow it, so that the stress occurs between the washer and its seat rather than being applied to trying to bend the bolt, accumulate stress cycles, and have a fatigue failure.
Reminds me of the super blend bearing.
Yes.
The roller bearing, we were having roller bearing failures in Nortons, and then also, Nortons of the sort of 70s, and the Ducati V-twin was having some issues, and super blends. It takes that straight roller, where you have perfectly parallel rollers. And
cylindrical, yeah.
Yes, perfectly cylindrical. So the sides are, cylindrical. And then the cases would flex, and the edge of that bearing would dig into the bearing surface, and it would go.
Because the crankshaft is trying to do this.
Yeah.
Because British parallel twins have no center bearing except for the AJS matchless. And so the crankshaft does flex at higher revs. And so main shafts are doing this. They're nutating. They're like the axis of a gyroscope when it's getting tired and wants to lie down. And that edge loads roller bearings. Well, why not use ball bearings? Because they have roughly a little better than half the load capacity of a roller. So you think to yourself, well, let's relieve the edges of the outer ends of the roller just enough that it would accommodate that degree of crankshaft flex. We're not talking about 1/8 of an inch or something huge like that. We're talking about something quite
it's
small.
just like some kind of radius instead of
They can make any profile you want on those rollers.
And they figured it out, and we got those so that your dished washer surface just like that, giving them a little bit of ease to slide instead of bend or dig in and flake and cause problems.
A motocross dad came to me and said, my son must just rev the living dickens out of his 250 because he said, I can't keep main bearings in it. And I said, well, what do you think's happening? And he said, well, it's like I tried putting rollers in there and the edges, they flaked off. So I said to him, just being, recreation can be such a thing as reading a bearing catalog because there's a lot of good information in there. How about using a spherical bearing? It has good capacity as a roller bearing, but the shaft can nutate and nothing gets overstressed.
Is nutate the new word that we're going to be, we have asperity.
It could be asperity and velicet.
Nutating. Yeah, velicets. TZ750s that go on.
Yep. So I spent 10 years with those TZ750. So there.
Well, reading the bearing, just to pause, I want to pause just to clarify. There are people, and then there's Kevin Cameron. And what does Kevin Cameron do for recreation? He reads the bearing catalog because there is a lot of great information.
You'd better read it.
Yeah, you better read it. And if you, it's going to the steel supply or the metal supply and reading the book that talks about the qualities of the metal. Like, well, what are you trying to accomplish? And you can read all of that stuff and you can say, well, you can wonder if you're working as I am on a Taylorcraft aircraft, putting a Taylorcraft aircraft together, and the guy who's assigned me at this place, this airplane hangar where I go with my son, he's assigned me to fixing the panel because I busted out my hammers and dollies to fix the backing plate and the brakes. So they're called shin brakes. And so they're these real mechanical, they're cable actuated brakes with this kind of horseshoe actuator. The linings are put on the inside of the drum.
So the linings rotate.
Yeah. And the shoes are just steel. They're just steel. And so you put all that stuff together. Anyway, he's assigned me, I was fixing the backing plates because they are lighter than a pie tin. Well, we're talking about like lightness of aircraft, just enough to get the job done. A pie tin, an aluminum pie tin, is heavier material than the backing plate for this brake. It's not mechanical. It's just a cover. And then the brake itself, the mechanics of the brake, it's like this kind of dog bone shape that bolts to the axle with 7 82-degree taper countersunk screws, blade, because it's 1937 or 42 or whatever, slotted screws. And then the mechanics are all there, and the plate just sits in between that dog bone that's made out of steel and that aluminum. But I had my hammer and dolly because the things were mangled. And so I'm smoothing them out and I'm fixing the flange, and we're just getting to know each other. And he says, well, you should work on this panel too. But what I'm getting to is like, you get to learn about what's it made of. Cause I like to weld and there's cracks in this panel. I'm like, well, I should weld this. And I asked him, what's the panel made of? Because it's aluminum. It's a very thin aluminum. It's probably, 30 thousandths or something. Also very light. And he says, I don't know. I said, is it 1100? Because I know I can weld 1100. 3003 H14, I could weld that. And it also it age hardens. 3003 gets better with age. Gets, like you build your body work out of 3003 and it'll stand up. Give it a little rest before you put it on your bike.
Precipitation hardening.
But you know what the numbers are because you read the catalog. And if it's 2024, which is a very popular aircraft aluminum, you can't weld it. It
Because it
just
has
won't.
so many alloying elements that when you try to weld it, the what do they call them? Heteroatoms move to the center of the weld and become a defect.
Yeah. And you just, so it's, and then you learn about numbers by reading the catalog because 2024 was just what it was. And then they go up the chain. It's 20, whatever it is. And it's 20 and it goes along and they've added more elements and it's stronger for this. And you get to learn about the manganese and the other things that they put in to get those qualities. So read the catalogs. That's what I'm saying. Read the bearing catalogs, read the metal catalogs, learn about it. Figure out what the metal is used for. This is what Kevin's good for, is because he'll be like, oh yeah, they made those pistons out of RR56. That was the Rolls Royce alloy and it was the 56 recipe. That's like, oh, hey, that's pretty good to know. I like it.
Well, RR58 was used
That's what
until
it is. Yeah.
like 1998 in GP racing and Formula One. So it was good stuff. And not that there aren't better alloys now, but the thing is, you get to know how to work with something. You know what to expect from it. So it's an old friend. Can you replace an old friend with a new friend? If you have to, I suppose you do it. But that causes people to cling to old standards. And for example, I wanted to make gears. And I did some reading and I found out that for small gears, 8620 steel is a good material because it can form a relatively thin case hardening and be heat treated to have a tough core. Well, later I learned that Yamaha used 8620 to make connecting rods for all their two-stroke stuff for those same reasons, because what had to bear on the hardened surface? Needle rollers.
It's this is reminding me of one of my favorite moments is when we went to go see Byron Hines with the first Harley V-twin
Yes.
drag bike. And we got access and we had Byron, right? Byron Hines.
Yep.
I mean, the metallurgist and designer, and they're in there making this thing from scratch because it had to be a push rod thing. And it was like, whatever it was, 2,200 or 2,500 cc's. 2,600 cc's, yeah. Ridiculously large, big, huge cylinders and the push rods of a certain length. And you were having a conversation because they had handfuls of parts. We were at a test. They were running it down the strip. And then Kevin's talking to Byron and he's holding up the parts and you were asking him like, oh, is that, 8620 or is that this or that? And he's like, well, no, it doesn't need to be durable. It needs to be tough. And that was the conversation. And it was the quality of the material that was being used. It wasn't like necessarily a cased hardened piece because they didn't need that. It just needed to be really durable for a short period of time. Like it needed to be tough, not necessarily durable. It didn't need to last 46,000 miles. It needed to last a quarter mile plus, or maybe to the next run or whatever it needed to be. And it's wonderful where you get that guy who's looking at all the recipes and making things out of
another similarity between motorcycles at high level and aircraft is that parts have specified lifetimes. And every part in a racing motorcycle has a specified lifetime. Wrist pins, pistons, rings, connecting rods, what have you. How many hours? When it's houred out, it has to be replaced. And in the aviation business, if you decide, well, it looks good to me, I think I can do another 100 hours. Is that good for business? We don't think so. So you're having to work within the capabilities of all these materials, processed in various ways that are well understood by specialists in that field. So it used to be, for example, that mnemonic 80 was a refractory material for making gas turbine blades. It was developed by the English, but it had this problem in that the grain structure, the size of the crystals in the material. See, all normal metallic material is polycrystalline. Now, my dad was of that generation that said, "Oh, look, it crystallized and broke." Nothing. It's already crystalline, so it can't crystallize. But what's going on there is that at operating temperature and under stress, the material is made of these zillions of tiny crystals oriented randomly. In those days, we came to oriented crystal materials, and then finally single crystal materials. You got trouble with the intergranular zones where all those crystals are stuck to one another? Get rid of the zones. Then you'll get rid of the trouble.
You should explain that a little bit more. Just that the turbine blade is now one giant crystal. Is that correct?
Yes, that's correct.
Yes.
And they're able to grow the crystal under very carefully controlled conditions so that it begins solidifying where they want it to, and it starts at a seed crystal that has been placed in the mold correctly oriented, so that when solidifying begins, that it begins from that crystal and continues with its orientation. Then there's a spiral passage that basically says this acts as a filter to make sure that that orientation is being preserved on its way to the actual mold cavity. And they are able in this way to produce these single crystal blades that are, they don't look different. They look just like, oh yeah, that's obviously a turbine blade, hasn't been machined yet. What's it out of? Oh, F100 or something. Well, the problem, of course, with jet engines is that they have to keep operating them hotter and hotter. And they finally got them to the point where during takeoff, the gas passing by which the blade is surrounded is hotter than the melting point of the material. But they have developed cooling methods that keep layers of cool gas flowing over the surfaces.
Boy.
There we are sitting back in our seats. Yes,
having a little sip of champagne or some tea,
And meanwhile, those hardworking turbine blades are whirling around in really hot air, hot combustion gas. So this is a process of development that has taken some time.
It is just a miracle, though. It really is a miracle that somebody decided to get rid of the intergranular zone or whatever. They just said, well, we can solve this problem by, and someone, they just worked on it and figured it out.
Well, if you've ever mixed concrete, you have some cement, and you have some sand, and you have some gravel, and you mix all that stuff together in a specified amount of water, and you can make concrete, like for a foundation. So in this case, it is as though the little stones in the gravel are the crystals, and the cement that is holding them all together is the intergranular zone. And the gravel in there is all randomly oriented in odd different shapes. And it's a workable material.
Well, it's why my garage, it's why my driveway is cracking, for one.
So. When you apply stress, repeated cyclic stress to polycrystalline materials, the little atoms that are um, under strain in some places because the intergranular material is trying to make a bond with other things that are nearby in crystals. It's under some strain. So at some point, that strain may be exceeded. Pop, that bond is gone. Now its load is being carried by its neighbors. And pop, pop. So there's all this trouble that goes on in the intergranular zone because basically you've got this massive crystals. This is what John Britton was talking about when he said, he said, when you've worked with directional materials as long as I have, ordinary metals start to seem like just really tightly packed sand. And that's what they are.
Yeah, it is. It's a big a big feeling of distrust. And what was the old saying about magnesium? Electrified dirt is what.
Yes.
So, the jet engine. I was going to say when we were talking about turbines and all that, and starting the podcast off and saying like how essential aircraft are, and we're a fan of piston engine stuff in my house. My son's 12 and he's a little pilot now. He's taking lessons and he's flown a 150 and a 172, and he's helping me with the Taylorcraft. He's really into it. He wants to understand. We like those. We like the propeller planes, and we're fascinated with jets, and we love our F-35s and all of that. But it's really the one thing that I think is we kind of derisively call jets vacuum cleaners because they just make the whirring sound, but they're awesome. And what I do love about a jet engine is the shape of turbine blades, how they've become these beautiful, efficient little swirls, like little.
Yes.
They're just really, they're so elegant and wonderful. So we do like the jet engines, but we're here for combustion in a cylinder, pop and then valves. What are you holding up there?
Well, that's an exhaust valve from an R4360, and
Kevin was once a collector of those. Just so you know,
I had 3 of them in my shop at a point.
They're not small. It's why I had a gantry crane, folks. You can't just pick a 4360 up. They're
1
huge.
pound per horsepower.
Yep.
3,500 for takeoff. This is a hollow valve, exhaust valve, and it has this very thick stem because it is hollow too. The head is hollow, and it is partly filled with sodium metal, which melts at quite a low temperature. Not this temperature.
Yeah.
But in service, the sodium rattles around inside there because the valve is moving, lifting, returning, and then sitting closed for a while, and then lifting, closing. And that serves to equalize the temperature of the part all over. Most of the cooling is between the valve and the seat, because the seat is a lot cooler than the valve, and the head is a lot cooler than the seat into which it is shrunk. So sending heat up the stem, you want the stem to be well lubricated. How hot can the lubricant stand to be? 350, 400?
Yeah, you don't want to coke your oil. It's
Nope.
It's a big problem in the exhaust bridge too. If you have little passages.
Yes, they have to be designed to drain after the engine has stopped.
It's like a turbo where they used to keep the fan running on the turbo, or you had a shutoff period where you had to idle the engine to keep cooling oil going through the turbo bearings so the bearings would cool off. And because if you just shut it off, it's just cooking in there. It's turning it into gunk.
And then no more circulation, which means that the exhaust bridge becomes very hot and it expands powerfully, yielding the material around it. And so then when you switch off and the magneto goes to sleep, the cylinder head cools, And that material that has been yielded is now too big for the exhaust bridge, which is placed in tension. We spoke before about how tension is the big problem. So there were some low performance air cooled 4-valve engines in the early days of motorcycling, of superbikes, and they were able to operate as long as they stayed away from making everything real hot and suffering exhaust bridge failures. That is, the material between the two exhaust valves. If you look at a Ducati cylinder head, turn it upside down, you'll see two large intakes, and then as far away as they can get from each other, two little dinky exhausts. And they're moved apart as far as they can for the obvious reason that the larger the exhaust bridge region is, the better it can conduct heat away to the rest of the head and not be hot enough to cause this cycle of tension, compression, pow, a crack forms. And this is a crack formation in cylinder heads. There's all sorts of special instructions for general aviation pilots in the use of engines in such a way as to avoid various forms of cylinder head cracking.
Oh, well, there's the Howard 500, beautiful, beautiful twin engine piston, high performance aircraft. The landing procedure coming down from cruise is pretty complex because you have to slow down slowly. You can't just shut it down because it'll shock cool the engine and it'll break stuff.
Yep.
You're up at high operating temperature and you're doing your thing and the engine's happy and it's all fine, but you don't just like shut her down. You got to bring her down nice and easy. It's like way far away from the airport. You're like, you got to plan this and you got to go through the procedure so you don't wreck your very complex and wonderful radial engines.
I talked to a gentleman who operated oversized aircraft. I guess he contracted with NASA and so forth and move large boosters and so on in these guppy airplanes.
Yeah.
And he said to me, the moment we bought our first turbine-powered airplane, I understood why the airlines got rid of piston engines so fast, just as fast as they possibly could, because he said, you've got the flight engineer's manual for the piston engine, and for the jet engine, you have the automatic system. You hit run, and the FADEC, fully automated digital engine control, FADEC.
Yeah.
And it handles it for you.
They're doing that with piston engines a bit now. You're getting where you just have a single thing. You're just like, oh, I want more power, and you just ask for it, and it takes care of all the business for you. It's not like your Taylorcraft or your Cub. Well, some Cubs didn't even have mixture control. Some of the J3s just had a carburetor that you didn't have mixture control. So the higher you went, the richer it got. Yep. So you got up to 7,000, things come. So that's not FADEC,
No, sir. Well, also FADEC is important because there was a time when the homeowner went out to mow the lawn for the first time in the spring. Engine wouldn't start. So he or she dumped the gas out, put fresh gas in, tried that. Still wouldn't start. Change the spark plug. Starts right up. Mows the grass. But a more modern technique is to buy a new lawnmower every spring because you can't make it start.
I was just going to say, who was your relation that moved the mower into the sun? And
that was my mother.
Got it hot. Yeah, your mother got it hot enough that it would start on the old gas.
That it would evaporate enough fuel. Yeah, once it got warm, and enough fuel would evaporate that it could be ignited by a spark and it would start. And she told me that. She said, "Well," she said, I thought I'd leave it in the sun for a while, and then it usually starts." Yes.
Well, Dale Wachsler, Wheels Through Time, the late Dale Wachsler, what a great guy he was. His son is running the museum, and he's obviously well versed in all this particularly old American stuff. So it's in Maggie Valley in what is that, North Carolina, and great museum. Dale was very good about what do you say, intelligent person and really well educated, but also the farmer guy, very
Yep.
experiential. Like he'd done so many things for so long, and he'd resurrected so many old motorcycles. And he was a big fan of the Sun and Aerocroil, unpaid endorsement. So Croil is this. It is relatively expensive, but it's in my experience, it's one of the best chemicals to use, penetrating oil to free something that's rusted or stuck. And he was a great freer of stuck cylinders, and he would hose the thing off with Aerocroil, and he'd get it in the bores, and he'd park the thing out in the sun and really get it hot. And then he'd break the cylinders loose, and then he'd work it really slowly. And he had all these motorcycles where he did that. And, the great Sun, we can rely on the Sun for some things, can't we? It's wonderful. Starting the lawnmower after now we just buy one, or it's electric and we change batteries every 36 feet.
This is why ultimately we have a big celebration at the time of the reversal of the seasons. Oh, it's getting colder. The days are getting shorter. What if it keeps on forever and we just freeze solid? Oh, now it's getting warmer. I think it's time to celebrate. And we do every year.
Something about entropy in there somewhere.
Yes. But we've got enough. We have a future because the Sun isn't gone that far along the progression.
Thank goodness.
One of the things that you'll notice is that cooling fins on air-cooled motorcycle engines are around 1/4 of an inch spacing. And at one point when Suzuki were trying to enter Grand Prix racing and make their bikes reliable, they were the first company to win a world championship with a 2-stroke engine. That was the 50cc. But if you look at any of the great radials, you will see that the cylinder fin spacing is much, much closer. I'm going to try to do this right now, wheel this thing out for you.
Sorry, Spotifyers, but we are doing show and tell. Here we go. Oh, look at those cylinders! Look at that. Well, that reminds me of GSXR 750 when they did the very close fin pitch when they were air oil cooled. Wow, that's remarkable. Now, well, you talked to me about this before, where there was a form like a guide, and they were cutting those with blades because you couldn't cast it so fine.
Well, this was a desperation move.
Yeah.
Because as we noted at the beginning of this podcast, it's cut and try. And when they got the 1820 engine, which powered all those B-17s, 14,000 something of them. It's a lot of B-17s. Of course, every time the takeoff power and cruise power are increased by development, there's more heat to get rid of, and so you have to have more fin surface area. Well, they were able to cast down to about 200 thousandths fin spacing. And that was rough because in making a 2800 cylinder that way, they had to set about 1,200 core pins to support the cores that simulated the airspace between the fins. A lot of work there, and it couldn't be automated. Could not be automated. Somebody had to, get the supervisor over here. I did it wrong.
Well, pattern making is its really its own art, and a lot of motorcycle designers relied. I don't know how it is today, but the guys I talked to who were doing this stuff 20, 40 or more years ago were really relying on the pattern makers at the casting place,
At the foundry, yeah.
at the foundry, to actually make it right.
Yes, the dimensioning, the radius, all that stuff was art.
Yeah, because you're
Before it
sitting
was
around,
science.
right? I mean, whatever. Dr. Taglioni is sitting around drawing it. He's not in the radius of the finning and saying that it needs to be a radius of 1.5 millimeters or something. That's the foundry guy. And even in porting, even in the way the design of the ports and the chamber, the final finished chamber, if it's not machined, was really a foundry thing.
Yep.
And they
So,
were, yeah.
what Suzuki did when they needed more fin area was they went to a finer spacing. With aircraft engines in the early days, the cylinders just stuck out of the housing around the crankcase into the airstream. Tremendous drag and bad cooling because the front of the cylinder was cooled well and the back of the cylinder wasn't cooled at all, because the air doesn't want to go through those tiny fin spaces. There's a boundary layer on everything that says, stop shoving on me. I'm sleeping here.
Well, and what are we trying to attain with cooling, right? When we were talking earlier, when we were discussing this podcast, the finning on the cylinder head is long and big, and as it tapers down to the bottom of the cylinder, it's quite short because it's not as hot as where the rings are,
where
at the
the
top,
fire is.
where the fire is, and that you're cooling. If you're air oil cooled, which everything was also oil cooled if it had oil circulating at all. We just didn't say it, but it was air oil cooled. You're looking to homogenize the temperature as much as is reasonable, and you're taking that oil and pumping it up into the cylinder head to lubricate the stuff, but also to cool it and to take the heat back down into the crankcase, which puts it up at a temperature that's closer to what the cylinder head is doing. And really your design is saying, like, yeah, we ended up in a temperature range that was good for the oil, and it was good for the metallurgy, and it didn't overstress the things, and the front of the cylinder wasn't super hot and the back cylinder isn't super cold, and we don't have dimensional stress and things that are happening. Like, it's kind of an art.
When they needed more cooling fin area, one way to get it was to make the fins deeper, and there are limits to that because aluminum is not the best conductor of heat. Silver is pretty good. Copper is sort of in between there, but aluminum is lightweight, and it was discovered during World War I that the ability to move heat per pound of material doing the moving was best with aluminum. So that's why cylinder heads are not silver. Also, of course, the tremendous weight. So eventually you could get to the point where the fins are so deep that the air can't reach the bottom of them. So the NACA, the National Advisory Commission for Aeronautics, did a 10-year study on how best to cowl radial air-cooled engines and how to cool them. And they found out that having the cylinder sticking out in the plain old airstream was the worst way to cool. And that what they ended up with was that if this is a slice through the cylinder and the air is coming this way, you had to have a baffle that fit right tight against the cylinder fins and went round to the back and only let the air out through a narrow passage. So it was open in the front for over 100 degrees, and the baffle wrapped tightly around so that the air had to pass through the hot fins at the back of the cylinder just as it had passed through the hot fins at the front.
And when you arrange the cylinders, so in a like a 2-row or 3-row radial, the reason they look like corn cob, they don't look like corn cobs, is because the cylinders are offset. So the first set of cylinders, they're ducted, and that's keeping the heat. It's extracting the heat from the cylinder here and the cylinder here, and then the next one in the row is isolated. It's not getting those hot cylinder air circulating. It's
baffled so that every cylinder gets cold air.
Fresh air, yeah.
Now, AJS built a V4 in the 1930s, and it was air cooled, and it was a V4 with the crankshaft transverse. So the aft cylinders overheated, and they got hot enough to encourage detonation, and detonation said, "I'm your buddy." And so in order to stop losing the top piston ring land and getting material eroding from the cylinder head, the first thing was they reduced the compression ratio, and they kept reducing it until they finally stopped the detonation at about 5.5 to 1. And then some wiseacre in the company said, well, in our last test, the V4, it's a 500, is barely any faster than our 350 single. Why are we doing all this complicated work? So eventually, they had to give up the idea of letting air come through the front fins and get heated up, and then that hot air trying to, in quotes, cool the rear cylinder. This is why parade mode exists. If you're stuck in traffic on a big V-twin, and it's one of those horrible summer days, just turn off the rear cylinder, turn off the spark, turn off the fuel injection, and just let it be itself. No combustion at all. And the front operates as a big single. There's a tut, 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 tut. You can keep up with traffic perfectly well and stop and go.
You hardly even notice.
Yes.
I'm not kidding. You hardly notice.
It's good. So that's one of those things that there have been several engines, motorcycle engines, that tried to cool the rear cylinders with hot air coming off of the front cylinders. And
Square 4, buddy.
Yep. The Ariel Square 4 and that Silverhawk strange V4 that was built earlier. It's a bad idea.
Well, we're going to talk about the Silverhawk because that's a Mecum. That's a bike that's coming up for auction. There is a Silverhawk V4 30s era, and it's a very interesting motorcycle. We'll talk about that on the podcast where we talk about the auction bikes.
Sure enough. So what did they find when they made the pitch of the cylinder fins closer and closer? They couldn't cast it. So then they said, okay, we've talked about this a lot of times. Now we actually have to do it. They began to forge the heads out of solid aluminum. And then they machined the fins. They machined the ports. They machined the valve pockets. Everything was machined. And they claimed that it was a savings of time over positioning 1,200 core pins.
I laugh because I'm a home machinist and I have a lathe and I have a mill and I do things and I build little tools and stuff. And I'm very proud and satisfied if I can make a dimensionally accurate top hat bushing out of bronze. You know what I mean? And to machine an entire cylinder head at a time when we didn't have 3D printers and we didn't have CNC 5-axis mills and CAD and everything.
They did have cam operated automatics, however, and that's how they were made, not by elderly machinists in octagonal metal framed spectacles holding up the micrometer. Well, make the next cut 1.2 thousandths deeper. Yeah. So it was a set it and forget it. The casting, the big forgings came off the machine. They got rough machined. And then what did they find? The reason that Suzuki's little motor with very closely spaced fins was never seen again is because it wouldn't cool. the bike went too slow to force air through those fine fin spaces. So on these machines with forged and machined heads, another reason for all those baffles to be there is to make sure that of all the air that's let into the front of the nacelle has to pass through fin space. Every cable, every hose, every bundle of wiring had to be sealed through those baffles so that it didn't produce a leak. And then they could cool these huge engines, making as much as 3,700 horsepower, 3,800 horsepower for takeoff at the very end. And they could do so by making sure that they had the highest possible pressure in front of the cylinders and baffle arrangement. Enough pressure to push the air through those fine fin spaces. And that's why B-29 crews were required to not climb for some time after takeoff if they were carrying a maximum load of fuel and ordnance, because it would be too laborious for the engine and the climbing speed would be reduced such that it would reduce the flow of cooling air through the cylinders. So all of this material was not taught to young farm boys to become flight engineers. It got converted into a bunch of slide rules that would enable you to compute how to stay on the safe side with these monsters. And it's quite a wonderful thing to imagine taking thousands of people who never dreamed of flying, much less being a flight engineer, and making them able to do a fairly good job.
Remarkable.
There were some exceptions, of course.
Yeah.
I
love the manuals of those of that era. When I read, like, I have a Jacobs kind of engine maintenance and repair manual, and it's not a huge thick thing. It's Jacobs is a 7-cylinder. It was on Cessna 195s for sure.
Oh yeah.
In a 300 horse, typically. They had one that was a little bit less power than that, but typically a 300 horse. And it's beautifully written, and the clarity is something else. This is not artificial intelligence. It's not 60% accurate. It's 100% accurate. And it's beautifully done by humans. And it's great. We've talked about this before, and we did a podcast on books and talking about particularly like the technical writing of the 40s, 50s. This stuff was very, very well done. Beautifully constructed language, very clear, easy to understand. Usually.
Because if they didn't, people wouldn't understand it.
They wouldn't understand it because we're just like, hey, you're out there doing whatever you're doing as a 19-year-old in Iowa, and you're, driving the tractor, or you're doing whatever your job is as a 19-year-old, and then you got to go get in a B-17 or a B-29, and here's your book, and you've never done it before. So.
One of my favorites is that if you look at the pistons that Shoichiro Irimajiri put in the 50cc Honda Twin Grand Prix engine, 1965, the skirt height in relation to the bore is about 60%. And when that era started, the skirt was like 1.3 times the bore. They were real old-time tractor pistons in those early Honda 4s. So here was Irimajiri trying to take friction out, and he thought to himself, contact between the piston and the cooler cylinder wall is how the piston stays alive. So I can't do away with all of that contact. How much can I cut away and still survive? Air-cooled aircraft engines
don't make me
suffered the same problem because this is about 60% of this.
Yeah.
And
what's your piston out of?
This is out of a 3350.
Yeah, this is from a B25,
Okay, that's a 2600.
2600. It's 6 and an eighth
Yeah.
bore.
Well, they used one basic cylinder arrangement for the 1820, the 2600, and the 3350. In fact, when the 3350 was being developed, they used 1820 cylinders for as a first try, and they had to go through 5 different iterations of cylinder design because it is cut and try.
Well, there's a real, I mean, this is what happens in motorcycle development. You take a company like Polaris, who's making all kinds of different engines for different wheeled things, side by sides, and I don't know, buggies and all that, and then motorcycles, and they've done the work on the combustion chamber. They know that this combustion chamber works. And so when they're starting out with a new engine, it's like, yeah, let's put that and use this valve arrangement, and away we go.
This is what nature does.
Yeah,
nature is very economical. Anything that's working well is continued in the next model.
Indeed. Well, I want to get we're kind of getting close to a time where we normally say we're moving on, but I want it. So we've talked about cooling and all these other things about oil and cocaine and things that happened in aircraft engines that helped us in motorcycling. If it's at all possible, let's briefly, he says, talk about the evolution of metallurgy, because it was really what drove the possibility of everything, and that what we got out of a 1936 knucklehead was really a result of some development in aircraft and the metallurgy that allowed us to get into the modern era.
Well, they started to use roller tappets, which are in every big radial. And they go back to Manley's engine that he was building for Langley's aerodrome, which was his effort to get into the air before the Wright brothers. Not that he knew that they were working, they were quite secretive. But Manley saw that this cam ring that he decided to use, which had cam profiles every few degrees all the way around it, it had concave places, which meant that a flat tappet couldn't work. So he thought to himself, I'll use a roller because it will fit in a concavity, provided that its radius is smaller than that of the concave place. Good thinking. And so in the 1920s, around 1925, Harley adopted roller tappets in their racing singles. And those roller tappets appeared in production in 1929 on the D model flathead, and then the W, and then the K model, and finally the Sportster. And in the Sportster, it has the 4 cams all geared together, just like in the D model. Those roller tappets come straight from aviation. All those rotary engines, a good chance, if you look at one, that it has roller tappets. So these similarities are not by accident, because similar solutions to similar problems. Now, motorcycle engines started out with cast iron flywheels because the complicated shape of the counterweights and all the rest of it was easier to cast than it was to machine from solid. And when they ran those engines fast enough, the crank pin wallowed out. It became loose. So, we'll make the flywheels out of steel. RPM kept going up, and Robert Iannucci notes that there are a lot of G50 flywheels, which are soft, mild steel, holding doors open all over England because their crank pins wallowed out. So they had to go to alloy steel. And this kind of thing took place intensively through the 1920s and 30s. metallurgy had been an art, it had to be turned into a controllable science so that when you design a new engine, you could rely on the qualities of the materials you were using. It wouldn't be the result of somebody had a big argument with his wife on the weekend, came in Monday and did a batch of bearing steel that just failed all over the world. That won't do. You have to have these standards that are adhered to. You've probably heard about dreadful quality control in early Chinese motorcycles and scooters. It was a sort of a joke in Southeast Asia where they made big marketing efforts. But they didn't yet have these rigid industrial standards so that when you picked out a ball bearing, let's put a 6305 in there, we'll want a snap ring. That tells you, gives you the beginnings of the part number. And do you want standard internal clearance or do you want C3 clearance, which allows you to press fit the bearing onto something so that causes the inner race to swell, or you clamp the outer between crankcase halves, that compresses it and does away with some of the internal.
Well, and that press is a spec, and you can hear you will hear a bearing. I experienced this on an early prototype, not an early prototype, but a prototype motorcycle I was riding before it was released. And I was getting to ride this thing, and I'm making notes. I'm a motorcycle tester, and I came back in and I said, there's a sound coming from the rear wheel. And the engineer said, like, I was talking to the guy who was running the program, and he's like, Steve, get over here. And Steve comes over and he says, he's picking up a sound out of the back, back wheel, kind of a sound. And the guy's like, oh, Steve's like, yeah, we're changing the press on that bearing. It's making noise right now, but they'll change the bore ever so slightly. So when the bearing goes in, it isn't squeezed quite as hard, and the bearing will be to spec.
It has internal clearance.
Yeah.
So there's room for oil between the rolling elements and the races. And everywhere you go in making parts for machines, you run into materials that aren't up to the work. Castings that crack, hardened materials that spall, inadequate tensile strength, connecting rods that break near the small end. BSA Gold Stars were famous for this. Rod breaks, the piston goes up and pounds the valves shut, whether the camshaft will let them happen or not. And it ruins the head. The short end of the rod is whirling around, jabbing holes in the crankcase as it goes. It may even damage the frame because there's a place where the frame is woggled to clear the crankcase. If one of the holes forms there, the frame could be damaged. People used to say, when I stopped sliding, I thought maybe I could save the magneto. So, but well, that's the one Hoss Shea poem about the vehicle that was made so artfully that all the parts had the identical lives, which is ideal, of course. You'd want all the parts to last equally, so you're not having to constantly take your car apart. Oh, the steering shaft, that's timed out. We can't go on vacation. I have to change it. The one Hoss Shea, in the last second of the 100th year, it all fell into a pile of dust. Every part failed completely at the same time.
Sure.
So in design, you're having to work out the lives of these things. One tuner said, I had some crankshafts that cracked. I took them to the metallurgist. The metallurgist said, these are wonderfully hardened journals. This thing will run 100,000 miles, no problem, provided you don't exceed the manufacturer's recommended RPM. But he said, inside, the material is pudding. In other words, why are we going to put chromium and molybdenum and who knows what all else into this part when it doesn't need it? Nowadays, there's a rev limiter, which helps. So you give the problem a solution that is no better than it needs to be, because to do otherwise is to pay for something you can't use, which
Well,
is extra properties.
having a cast crankshaft in your Jaguar 3.8 liter inline six that you run to, 5,500, maybe 6,000 for special occasions if you take care of the rods. But really, 5,500 is what they rev to, and they'll do that a long time. Very long stroke. But if you want to make a lot of power and you want to make a race motor out of one of those and really rev them up, we're going to machine a crankshaft out of billet steel, something that is
4340.
that's going to be significantly stronger.
Yep. And have excellent fatigue properties as well.
And we'll replace the rods at the same time.
And it is the job of metallurgy to tailor materials to the applications. And if there's a sufficient market for it, a new standard will be written for that material, and it will join the inventory. And this is how an industry can exist, because there are all of these givens. All they have to do is put their finger on that key, and they know the note that will play.
It reminds me of the lessons that we keep on learning. We've talked over the years where Ricardo, High-Speed Internal Combustion Engine by Harry Ricardo. It's a great book. Go find one. You don't need a first or second or fifth, or just find any one. Buy it as cheaply as you can.
It's also on the internet. It's on the internet.
Yeah, just read it on the web. Why not?
It's non-mathematical.
It's a very good book, and it codified so much, and it was not read by people in the 50s who were still making engines that had terrible cylinder heads, terrible breathing, terrible combustion chambers. It just wasn't read. It was like the lesson that needed to be learned over and over again. And it reminded me of the era of Indian long before Polaris got it. It was sort of recycled and kicked around, and people would buy the name, and then they would try to do something, or they would take a Velocette like Climber did at the Climber Indians, where you had a Velo that said Indian on it. And one of the versions that we got was like Gilroy CMC era, somewhere around that time. And they got the name, and they were basically like custom bikes, and they would call, Baker drivetrain, but they didn't have a spec. They were just saying like, okay, I'm going to get that engine. We'd redesign these cylinder heads to make them look like this, even though it was a 45, like a Harley, basically a clone. And then the transmission we're getting from that guy, and the primary cases here, and there was no spec, and nothing would really go together. Talk about tolerance stacking, where, the spec is that it has to be somewhere in this range, but then it's this much, and then down the line, everything spreads out, and it just doesn't bolt together. And
just give every station on the production line a stack of shims.
Yeah. And so, there they are learning, and they learned the lesson. I know about this because the people who were doing it said, hold on a minute. They got in some manufacturing expertise, and that's where the story came from. Yeah, they were doing it this way, but now we have a spec. Yeah. And so when we give that to the transmission maker, it has to match this, and we check it, and then it bolts together.
Yep.
Well, that's it, folks. That's it for Aircraft 101 versus motorcycles. How did we get here? We know it's off the beaten path. It's not your TZ 750 podcast or your RD 350 or whatever. But it's something near and dear to us. We loved aircraft. We do love aircraft engines, and Kevin's been studying this stuff, and he's got big note cards, thousands of pages of notes about metallurgy and where
sort of embarrassing.
Well, an embarrassment of riches, let's say. I've heard that before.
Let's hear it for that.
But we thank you for listening. We also thank Mecum once again for sponsoring the podcast, and a couple more coming up. Tune in, go to the auction if you can make it. And it's late January 27th through the 31st. It's a wonderful experience. You can see everything. You can stream it afterwards, or you can watch it and bid remotely and all that. It's exciting to be on the floor, to be honest. It was great. We watched a bike cross the block for more than $1 million at the end of that auction. It was really something. So very exciting, and also some bargains. So thanks for listening, and we'll catch you next time.